So, in the last video we have seen how to solve a Bessel equation, and we have seen certain properties of Bessel equation based on the. So, one of those are using those two properties we have shown we have given the orthogonal property of Bessel functions of first kind. Okay. So, those solutions of Bessel equation which are bounded at 0. So, today we will just have we will relook into these properties and then make use of them to show that to find all the j half, j 3 by 2, right. So, we also have seen j half and j minus half as nice explicit analytical expressions in terms of sine and cosines, and once you know j half and j minus half, you can get j 3 by 2, j minus 3 by 2, j minus 5 by 2, j 5 by 2 and so on. Okay. So, all j half of the odd n plus 2, 2n plus 1 divided by 2, and is running from 0, 1, 2, 3 onwards. All these things you can get it just if you know j half and j minus half, that we know as analytical expressions. Okay. So, this we make use of the properties of Bessel functions, and then we can get all these j 3 by 2, j minus 3 by 2 and so on. Okay. We will look at that. So, consider the Bessel properties what we had. Look into the Bessel properties. So, these are ddx of x power alpha j alpha of x. This is given as, which we have shown already. So, x power alpha comes out j alpha minus 1 of x. This is one. If you actually differentiate, which you have seen, x power alpha j alpha dash of x plus alpha times x power alpha minus 1 j alpha of x. So, I just expanded the left hand side, and right hand side you have j alpha minus as it is. Okay. So, now you cancel both sides x power alpha. So, what you have is j alpha dash of x equal to alpha by x j alpha of x plus, so minus of this if you bring it this side, plus j alpha minus 1 of x. This is 1. So, this is the property 1, and you also have the property 2, that is a derivative of x power minus alpha, you multiply to the j alpha of x, and if you differentiate, what we have seen is x power minus alpha comes out with a negative sign, and now you have j alpha plus 1 of x. Again you do the same thing, expand the left hand side. If you do that, x power minus alpha j alpha of x, and this will be minus alpha x power minus alpha minus 1, okay, into j alpha of x equal to x power minus j alpha plus 1 of x. Now, you cancel both sides x power minus alpha. So, what you have is j, this is actually derivative, okay, j alpha dash of x equal to alpha by x j alpha of x minus j alpha plus 1 of x. This is what you have. So, these are these are the properties. These are nothing but same as the properties of these Bessel functions, which we call 1 and 2. If you add and subtract them, so addition will give adding these two. So, let us say adding these two, addition will give you what it gives you addition. So, if you add it to j alpha dash of x equal to, so this goes, and what you have simply is alpha minus 1 minus j alpha plus 1 of x, that is 1, okay, and subtraction gives you. So, if you subtract it, so the derivatives goes, what you are left with is simply 2 alpha by x j alpha of x minus j alpha plus 1 of x minus okay, minus j alpha minus 1 of x. So, this minus this plus that is this minus of this and minus of this will give me this one equal to 0. So, this is nothing but what you have is simply j alpha of x equal to 2 j alpha of x. Okay. Subtraction will give you this 2 alpha of x equal to x times j alpha minus 1 of x plus j alpha plus 1 of x. Okay. So, this is what you have. So, this is the second, these are, you can call them as recurrence relations, okay, for the first kind Bessel functions. Okay. So, we make use of this, we already know j half of x, we already know what it is, and similarly j minus half also we know. In the last video I have seen that this is root 2 by pi, j minus half is cos x. So, this is sin x, pi x sin x, okay, and then j minus half is root 2 by pi x cos x. So, once I know this nicely as analytical expressions, so now I make use of this one, the second relation that will give me j minus. So, if I put here, so if I take 2 times j alpha of x, I take this second relation x times j alpha minus 1 plus of x plus j alpha plus 1 of x. Okay. So, here you put alpha equal to half, what do you get? So, you get j half of x equal to x times, now you have alpha is half, j minus half of x, and the third one will give you j 3 by 2 of x. So, this will give me j minus j 3 by 2. So, I can get j 3 by 2 of x in terms of j half and j minus half, that is 2 by x j half of x minus j minus half of x. So, this is my j 3 by 2. So, if I put alpha equal to minus half, okay, then what happens? You have j minus half of x, which is equal to x times, now if alpha is minus half, so this is j minus 3 by 2 of x plus j half of x. This gives me j minus 3 by 2 as 2 by x j minus half minus j half of x. So, like this I can go on. So, having known j 3 by 2, j minus 3 by 2, now I can put j alpha as 3 by 2, okay, plus or minus 3 by 2, let us say. Then you can get j plus or minus 5 by 2, okay. So, you can get like this and so on. So, you can get 5 by 2, 7 by 2, 9 by 2 and so on, okay. So, this is how you can get all j 2n plus 1 by 2 of x suffix, okay, for every n 0, 0 is known. So, you can get 1 if you put, so 0, 0, 1, 2, 3 and so on. So, everything is known, okay. So, these are Bessel functions. This is how you can get all this special case of the case 2, that is where 2 alpha is odd integer. This is the case, you could see that j alpha, j minus alpha are as series solutions. So, you can also get them as a nice expressions, analytical expressions in terms of cosines and sines and root x's, okay. So, this we will move on to Sturm-Liouville theory. So, this is the, so far what we have learnt is you know how to solve second order when you have a second order homogeneous equations with variable coefficients. When you look at 0 is a singular point, regular singular point. So, you can find the two linearly independent solutions, okay, because you see the Bessel's equation, 0 is the only singular point, there is no other singular point, okay. If so, the whatever you calculated, you find these Frobenius solutions y1 and y2, they are actually absolutely and uniformly continuous, uniformly converging as a series. These series are actually converging uniformly within the interval, any interval you take for all x positive, because there is no other singular point. Suppose for certain equations 0 is a regular singular point and there may be some L is a regular singular point, and this side let us say some m is minus m is a regular singular point. Then the way you calculate from this Frobenius method, you get this y1 and y2, these Frobenius series solutions converge absolutely and uniformly from this point to this point, whichever is the minimum. You calculate this distance, this is m, you calculate this distance L. So, these are the regular singular point, even some singular points, forget about regular or not. 0 is a regular singular point, L and m are singular points. If you know, now you can calculate for x positive. If you calculate for x positive, you look for solutions. You look for solutions for x positive, you get y1 and y2. What you see is up to the next singular point, that is L. So, y1 and y2 are valid between 0 to L. So, this is the theorem without proof. So, you have this y1 and y2 are finite whenever you have x is within this next singularity between the 0 and next singular point L. So, between 0 to L you have your solutions are valid, because for Bessel equation there is no such L is infinity. So, for all x positive your solutions are valid. Similarly, for the negative side, okay. So, just for the sake of completeness we can write your solutions j alpha of x and whatever j alpha of x for the negatives, for this is defined for x positive. What happens if x is negative? X is negative, you can write j alpha of x for x negative is actually, you can write this is given as summation n is from 0 to infinity x power alpha x by 2 minus 1 power n, okay. So, this is what is your xj minus 1 power n x power 2n plus nu 2n plus alpha, okay, by 2 divided by n factorial and gamma of n plus alpha plus 1. So, this is what you have. So, here if you remove this n is 2 power n's, I can make if it is negative or positive does not matter, but I have a problem if I have x power alpha. So, this alone you can write into x by mod x by 2 power alpha for x negative. So, this is how you should look for your solutions. Always look for solutions in this fashion in the Frobenius method when x is negative, okay. So, that means you always look for your solutions in this fashion. So, either this way. So, initially you look for solutions mod x power alpha power of k, okay, into power series solutions Cn x power n and y2 of x depending on the case you may have. So, you may say for example, in the case 2 you can write some arbitrary constant and y1 of x, this is for x negative, y1 of x log x now is not defined, it's defined only for positive values. So, now you are defining for x negative. So, you have to take mod x plus x power, so you power of alpha, that is k2, right. So, you have this is for k1 which is bigger root, if you want k2, so mod x power k2, now you make a sum. So, n is from 0 to infinity some dn x power n. So, this is how you should look for solutions in the negative interval, okay. So, with this we will move on to Sturm-Liouville theory. So, this is how you can solve any second order linear you can actually solve second order linear homogeneous equation. So, you can find two linearly independent solutions. Once you find two linearly independent solutions, okay, you know if it is if your equation is having a right hand side, it is a non-homogeneous term, you can find a particular solution by the method of variation of parameters. Okay. So, with that method you can find a particular solution and then you combine with this general solution of the homogeneous equation to get the general solution of non-homogeneous equation. This is what we have seen. So, we will start with the Sturm-Liouville theory. Sturm-Liouville. So, what is this theory about? So, what is the Sturm-Liouville theory? See, so far we have a general equation. General equations are a naught x y double dash, second order equations, a y double dash plus a1 x y dash plus a2 x y equal to 0. So, depending on whether zeros of this a naught of x are singular points or not, if zeros of a naught of x, if they are regular singular points, okay. If there is no zeros for a naught of x, suppose a naught of x is non-zero everywhere, I can divide it, I can actually get the power series solutions. There is no other singular point. So, power series solutions, if you look for, you can get the power series solutions everywhere for every x in R. Okay. I can get both y1 and y2, two linearly independent solutions, then I can solve it, I can write the general solution as linear combination of this y1 and y2. What if, so if a naught of x is 0 at some point, at certain points, okay. So, they are singular points, we have seen already. So, around that singular point, if it is a regular singular point, if the point is singular point is regular, then you can look for from either side of the singular point, you can look for solutions as a Frobenius series solutions. Even so, even there, if these are the two singular points, I can look for solution in this interval and I can get two linearly independent solutions by the Frobenius method in this, which is valid in this interval. Again, you can write the general solution of this homogeneous equation as a linear combination of those two linearly independent solutions. Okay, I can get the general solution. So, basically I can solve this second order equation. Okay, maybe for all whole interval or whole real line or some part of the intervals where it is defined. Okay. Then what is this Sturm-Liouville theory? This actually what we do is we try to make this equation, okay, as some operator, let us say a differential operator L y equal to 0. So, imagine a matrix, L is like a matrix y equal to 0. Okay. Then this is this matrix, this operator L is L, I can always put it in the self-adjoint form. Okay. What is the self-adjoint form? We call this self-adjoint form. We can always put in this form, self-adjoint form. We will see what it is. What is the meaning of self-adjointness? This is like if you see L is, I said L is operator, differential operator. So, you can think of L as a naught of x d square by dx square plus a1 x ddx plus a2x. It's clearly this is what it is. Okay. So, if I put this L in the self-adjoint form, this is not the self-adjoint form. So, this is what we have already, my, it is called this my. Okay. My is this, where m is this. Okay. Now, this m I can rewrite and put it in this form Ly equal to 0, where L is a self-adjoint form. So, before I say what is the self-adjoint, you imagine it is like L is like a matrix. So, you have a matrix Ax equal to 0. Look at the matrix equations. Okay. This is the differential equation, this is the matrix equation where A is the n by n matrix. Okay. N by n matrix, X is the n by 1 vector. Okay. And you have this, you want to see what is this A. If A is, so I am saying I can always make this my equal to 0, this differential equation I can always put it in this form, which is self-adjoint form, that or Hermitian form. We call this Hermitian Hermitian, if you see, if you look at the, you know what is the Hermitian of a matrix. If A is the matrix, let us say let A be a Hermitian matrix. What is the meaning? So you take this transpose and then you make a bar which is equal to, that is how you write A star. This is actually A star, you can denote. This is same as A itself. If you have a real entries, this is nothing but A transpose equal to A. If your matrix is having only real elements, A transpose equal to A. Okay? If your matrix is having complex numbers, then the bar makes sense. So, A transpose bar, that is A star equal to A. So, if this is the meaning, this is the definition of Hermitian. So, if this is true, you have this matrix is Hermitian, okay, or self adjoint, or okay, or self adjoint matrix, self adjoint matrix. Okay. So, what are the properties of this matrix? If you actually see the properties of this A, self adjoint, this Hermitian matrix A, okay, of a Hermitian matrix. Thing is, you can see once you have this self adjoint matrix, that means A transpose equal to A or A transpose bar equal to A. If you have such a matrix, if you calculate its eigenvalues, okay, you know what is the eigenvalue? Eigenvalue of a matrix A is A minus a lambda, lambda is an eigenvalue, you make a I, this determinant equal to 0. So, this all the roots of this polynomial equation, A minus lambda I is identity matrix, n by n matrix. The determinant equal to 0 will give you n roots of this equation, that is you may have n roots, they are same or they are distinct or same, can be same, some of them can be same. So, you will have, because it is n by n matrix, this equation determinant will give you nth order, nth degree polynomial in lambda. So, that will have n roots, lambda 1, lambda 2 and so on, lambda n. So, these are eigenvalues, because A minus you take any of this lambda I, any of this value of I, this as a matrix you take into x equal to 0. This will always have a non-zero solution, because the determinant is 0. For this lambda, the determinant is 0, that is what is the condition. So, determinant is 0, so you will have a non-zero solution, solution you can call this x, non-zero solution. Okay. So, non-zero solution is called the eigenvector, eigenvector is x, which is non-zero, and the eigenvalue is lambda I. Okay. You can call this I if you want, corresponding to I, you can call this lambda xi. Xi is the eigenvector corresponding to the eigenvalue lambda I. So, this is what you see. So, first of all, if it is a general matrix, this is the definition of eigenvalue and eigenvectors. Okay. If A is a general matrix, if it is a Hermitian matrix, eigenvalues are always real. You can actually show that. Okay. The first property is, you can check it, verify, eigenvalues are always real. That is the first thing. Okay. Eigenvalues are real, and eigenvectors you can, so once they are eigen, another property of the Hermitian matrix is, second important property, you find all the eigenvectors. Okay. If you actually calculate the eigenvectors for each of these eigenvalues, you will get, suppose all are distinct, lambda 1, lambda 2, lambda n all are distinct, then you will have n distinct eigenvectors. Okay. So, you will have n distinct eigenvectors if lambda is are distinct, okay, if eigenvalues are distinct. they are different from each other. Okay. If suppose they are repeated, suppose lambda 1 is repeated thrice, you can find 3 solutions. Suppose lambda 1 a minus lambda 1 I into x equal to 0 if you consider for lambda 1. So, because lambda 1 is repeated thrice, so lambda 1, lambda 2 is also lambda 1, lambda 3 is also lambda 1. In that case, if A is a Hermitian matrix, I can always find 3 linearly independent solutions for this system. So, I will have 3 linearly independent solutions for the vector for the matrix A, okay, for this system. For this system, you will always have 3 linearly independent solutions. So, that means you have 3 linearly independent eigenvectors corresponding to the eigenvalue that is repeated that many number of times. Okay. So, third point is you will have m linearly independent eigenvectors corresponding to an eigenvalue that is repeated m times. Okay. So, if you have an eigenvalue that is repeated m times, you can get m linearly independent eigenvectors. Again, once you have so the important property here is one more is observation. Once you suppose that all the eigenvalues are distinct, so you will get n distinct eigenvectors. Not only they are linearly independent, they are orthogonal to each other. Okay. So, distinct eigenvectors are all orthogonal. What do you mean by orthogonal? Orthogonal with respect to, so what is the meaning of orthogonal? So, suppose you have 2 vectors. Okay. So, let us write 2 vectors x and y. Okay. X, y are orthogonal if this is the definition. Okay. If x dot product with this vector dot product. Okay. So, what is the vector dot product? If your vector is having only real entries, you can simply have xi, yi. If you have a complex entries, you can just make a bar. Okay. That is I is from 1 to n. So, this is what you have. So, this is the dot product. So, this is the dot product you can call that you can with the notation you can write x comma y in this bracket if you put it, which is actual by definition this is the dot product of y. Okay. Notation, this is just a notation. So, if you have a Hermitian matrix, all the eigenvectors which are distinct all the eigenvectors corresponding to distinct eigenvalues. Okay. Eigenvectors corresponding to distinct eigenvalues, you should say. Eigenvectors corresponding to distinct eigenvalues are all orthogonal. So, that means if I have all are distinct, you take any one of them. So, lambda 1, lambda 2, these are all distinct, lambda n are eigenvalues. Okay. Now, corresponding eigenvectors, let us call this let us call this as V1. Okay. V1, V2, when I write V, small v, that is actually represents the vector. Okay. V1, V2, Vn, these are all eigenvectors distinct. Here these are all distinct, none of them are each other same. Okay. So, there nothing is repeated here, they are all each if you take any pair they are all different from each other. So, you have these eigenvectors, they are all orthogonal. So, that means you take any Vi dot product, that is dot product. Now, we have a notation, there is Vj, this dot product which is Vi dot Vj which is 0 for every I is not equal to j. That is what is the meaning. Okay. So, if this is what is the property, you can write it as property 5. If let our eigenvalues that are distinct and these are eigenvectors, then this is true. Then you see that all the eigenvectors are orthogonal. That is what is the meaning of orthogonal. So, orthogonal means this is true, this inner product this dot product which I represent with this. Okay. So, this is what is the case. So, what if they are repeated? So, the last point is, what if they are repeated? If they are repeated, suppose say lambda 1 and another one lambda 2 equal to lambda 1, okay, and then lambda 3 and so on, lambda 4, lambda n. So, only lambda 1 is repeated twice, okay, or eigenvalues. And then corresponding eigenvectors, I know that V1 is an eigenvector, V2 is an eigenvector, two linearly independent, these are two linearly independent vectors, okay, vectors corresponding to lambda 1, and I will have V3, V4 up to Vn. These are all eigenvectors corresponding to distinct eigenvalues. So, what happens? These are all, if you consider any pair here, they both are orthogonal, okay. Any pair is orthogonal to each other, but these are not, okay, these two. But you can make them if they are suppose you consider two vectors here, if they are like ij, x axis and y axis, they are already orthogonal, their dot product is 0, 1 0 and 0 1, okay. And if they are like this, if your vectors are this one, V1 and V2, so you can always make them orthogonal this way. You consider, so by just a notation you call them, so let us call this U1 is one vector, U2 is another vector, which is, they are not orthogonal clearly, you can see that U1 and U2 are not orthogonal. So, you want to make them orthogonal, you define it like this, U1, okay. I want to define now, you take V1 as U1, okay, this itself is V1, and what is your V2? I want V2 in such a way that I want to take a linear combination of these two, your U1 and U2, so that is orthogonal, that is my V2. V2, I want a linear combination of this and this. How do I do? You will see this, V2 equal to, so this is called GramSmith orthonormal process, okay. So, how do I do this? Simple thing, this is V1, okay, which is U1 minus some constant. So, let us say some constant times U2. Simply take the linear combination with some arbitrary constant C. So, I want to find this, I want to choose this constant C in such a way that V2 is orthogonal to V1, okay. That means V2 inner product you take with V2 itself, okay. If you take this becomes V1 V2, and I am choosing my C in such a way that this is 0. So, this is 0, okay. So, this is 0 and then C equal to, so let us say V2 is some vector which is already orthogonal to V1. So, that is what is my V2, okay. So, if I want such a V2, what is my C? That is what is the point. So, V2 you choose in this fashion, V1 plus C times U2, okay. Then you have C times inner product with dot product with V2. So, I have chosen my V2 in such a way that this is 0, okay. So, this is equal to simply C times U2 V2. So, this means C equal to simply I will have V2 V2 divided by U2 V2. So, with this C, if I choose my V, V2 is orthogonal to V1, that is the meaning, okay. So, that implies V2 equal to V1 plus V2 V2 divided by U2 V2 into U2. So, you see that this is and V1 equal to U1. So, already U1, so the V1 wherever V1 is there, that is actually U1. So, I can write in terms of U1 U1. No, not like this. So, let's redo it. So, you choose C in such a way that V2 is orthogonal to V1. So, how do I choose this? You take the inner product with, you take the dot product with V1, then I will have V1 V1 plus C times. So, you are simply making the dot product with each of these left and right side, okay. Then CT times U2 dot product with V1. V1 is actually U1. So, and I want my V2 to be 0 for some C value, okay. So, if I want the left hand side 0, that can determine my C. So, this is equal to V1 V1 plus C times U2 V1. This implies C equal to minus V1 V1 by U2 V1. So, U2 I know, U2 U1 U2 are known. So, this is what is my C. So, with this choice of C, my V2 is V1 minus V1 V1 by U2 V1 into U2. You see that this and this are orthogonal to each other. That is, if you actually choose V1 V2, if you do that actually, so you will see that V1 and you take the inner product with this dot product. So, basically dot product, okay. So, dot product, I replace V2 with this V1 minus V1 V1 by U2 V1 into U2, okay. So, this is the dot product. So, this is nothing but V1 dot V1 minus V1 V1, okay. So, just repeating, divide by U2. So, if you want, you can write dot product as this V1 dot V1 U2 dot V1 into U2, okay. So, this is nothing but V1 dot V1 minus V1 dot V1 by U2 dot V1 into V1 dot U2. So, think of just the real values, you can see that this cancels, what you are left with is 0, okay. So, this is how you, what if these are if U and V, U1 and V1 are having complex entries, what happens? So, you see that V2 V1, V1 V1, U2 V1. So, this is what you have, that is fine, okay. So, if you have V2, you can rewrite if you want V2 V1, okay. If you do that, this you are making inner product with, you are making a dot product with V1. So, this is also same. So, this is the same as V1 V1 dot product with V1. So, it is easy to see if you do like this. So, this is V1 dot V1 minus V1 dot V1 by U2 dot V1 into U2 dot V1, okay. So, this cancels, what you are left with is V1 V1 minus V1 dot V1, which is 0. So, you see that V2 is perpendicular to Orthogonal means perpendicular to V1. So, that is what is the meaning. So, if you are given two linearly independent vectors even in the plane, you can actually, by this process, you can actually make them orthogonal. I can always look for V2 as a linear combination of this U1 and U2. U1 you choose as V1, linear combination you choose for some constant. That constant you can find out in such a way that V2 is orthogonal to V1. So, that is what I used. If I make it 0, I can find this my C. With this choice of C, if you put it here, you can verify that they are orthogonal. Now, I may have 3, I can make them orthogonal. Suppose you have 3 vectors, let us say you are in the space U1, U2, U3. U1, U2, I make it V1, U1 is V1, U2 is V2. Now, U3 is also you can make. So, I can now take U3, I want V3 as a linear combination. Now, you have a V1 and V2, V1 and V2. Now, the third vector is V3. This I want another V3. So, I look for V3 which is orthogonal to V2 and V1. But I write in terms of V3, I write in terms of V1, V2 and U3. So, once I have V2, I can remove this U2, gone. Okay. So, I have V3, I want another perpendicular vector. So, if I look for such a thing, I can always look, I can rewrite as a linear combination of V1, V2 and U3. V1 and V. So, how do I do this? So, V1 plus C1 V2 plus C2 V3. No, there is no V3, so you have U3. Okay. So, again you want, what is this, how do I find these constants C1 and C2? See, I have 2 constants I have to find, right. If I look for V3, I choose V3 in such a way that which is perpendicular to V1 and V3 is also perpendicular to V2. So, I have 2 conditions here. So, these are the conditions. With these 2 conditions, I can get 2 constants. Okay. So, with these constants, if you do that, you can find these 2 constants. That, so, whatever you come back and substitute here, I can get V3. Then V3 is the way you get that V3 is actually perpendicular to V1 and V2. So, like this you can go on, get any number. If you have n linearly independent vectors, you can do this process and create, you can make them orthogonal. That means they are perpendicular to each other. Okay. So, such a thing you are doing. So, you have this. So, what you have is, so you can make them, you make them by that process, by the above explained process. This is called the GramSmith process. Okay. Make them orthogonal by the GramSmith orthogonal process. You can make them. So, by this process, this is just explained the space or in the plane. Okay. So, this you can do in any finite dimensional space. So, if you can do this, you can go on. Okay. Any given linearly independent vectors, you can actually make them orthogonal. Okay, by this GramSmith process. Okay. Only thing is, you have to find every time. Once you get now you have V1, V2, V3 are orthogonal. Now, suppose you have one more vector, you make them one more time. V4 is V1, V2, V3 are already orthogonal now. So, now you make a linear combination V1 plus C1 V2 plus C2 V3. Now, you have one more vector that is not orthogonal, that is U4. You write C3 U3 U4. You can get this C1, C2, C3 because you want V4, which is our condition is V4 has to be linearly independent with V1, V4 has to be orthogonal with V1, V2, V3. So, those are the 3 conditions. You have 3 unknowns, 3 conditions, that is V4 V1 is 0, V4 V2 is 0, V4 V3 is 0. So, with these 3 I can find my C1, C2, C3. What you get is V4, that is orthogonal to V1, V2, V3. Now, I make U1, U2, U3, U4 as orthogonal vectors V1, V2, V3, V4. In that V1 is nothing but U1 itself. Okay. So, that is how we do this. This is a GramSmith orthogonal process. Okay. So, this is what you see if your matrix is Hermitian matrix. This is important. Okay. So, not only this, any vector. So, this is A is n by n matrix. So, once you have a Hermitian matrix with these n orthogonal vectors. Okay. So, you can get n linearly n eigenvalues, either repeated or not repeated, distinct, either distinct or they may be repeating. In any case, you have n linearly independent eigenvectors. If they are distinct, they are actually they are nothing but they are directly orthogonal. If they are not orthogonal, you make them orthogonal. Okay. So, they always have if you have n eigenvalues for any matrix, if it is a Hermitian, you will have n linearly independent eigenvectors. You make them orthogonal. So, in any case implies you have n linearly independent n orthogonal. Orthogonal means obviously they are independent. So, n orthogonal eigenvectors. Okay. So, once you have orthogonal vectors, any vector you take any x in Rn, I can write in terms of all these eigenvectors, all these orthogonal vectors. I can make them some linear combination of these Vi's, I is from 1 to n. So, this is true for any x, I can write, we can have this representation. Okay. Because any vector I can write in terms of ijk in R3. In the plane, any vector I can write in terms of ij. So, same way any vector here in Rn I can write in terms of these Vi's which are orthogonal. Vi's are looks like ijk like that in R3. Okay. So, this is what is analogous to this matrix. What we do is we convert this equation my equal to 0 into a form that is called orthogonal. So, there is a Hermitian form we have to make Ly equal to 0. Okay. We can always do this because I can convert any second order equation into this form. So, the differential equation is always I can make them Hermitian, we will see that. Okay. So, I can always make them Hermitian. Now, because analogous to this matrix which is Hermitian, you have all these properties. The same thing you can do here also. Okay. So, here is because it is a matrix, the solutions are only finite. The solutions are all vectors. Vectors are in the finite dimensional space, that is Rn, either space or plane. Okay. These are all 2 dimensions is a plane, 3 dimensional it is space. Okay. So, if you n equal to 3 you are in the space, n equal to 2 you are in the plane, otherwise it is a finite dimensional means n is finite. So, once you have this, you have n linearly independent n orthogonal vectors you can always get. But if it is a differential equation, the solutions can be their functions they cannot be in a finite dimensional vector space. Okay. They are not finite dimensional vectors. Each vector, so let us say 1 x, x square, x cube and so on, you have infinitely many they are all linearly independent. If they are solutions, they are also okay. So, because they are all infinitely linearly independent, so independent functions. So, the space you can call this just like imagine your Rn, it is like R infinity. So, you have infinite dimensional space. Those functions belongs to this, just polynomials themselves belongs to infinite dimensional space. So, in general if you talk about general functions, exponential, all this, they actually form infinite dimensional space. Okay. So, the solutions are also belongs to infinite dimensional space. So, if you have a Hermitian form of that differential operator, differential equation, now what you do is you analogous to these properties of a matrix, you find the eigenvalues, eigenvectors and make them orthogonal, and then so that you can write at the end like this, any function in the infinite dimensional space I can write in terms of these eigenvectors. Okay. That is actually our Fourier series. This is what is a Sturm-Liouville theory. So, that is what we will see. Okay. So, first of all I have to make how to make a general second order differential equation in this form. Okay. Okay, so the main idea is to make this equation into self-adjoint form or Hermitian form. So that we will see in the next video. Okay. So we will see that how to make the second general second order homogeneous equation into self-adjoint form or Hermitian form. So in order to do this, if it is a matrix, you can easily see it is just the entries A transpose equal to A or A transpose bar equal to A. That is what you have to see. But for a matrix, for a differential equation, if you want this to be in the Hermitian form, you need certain boundary conditions. So for if you want a boundary, what is the domain? Domain is full R. So you want if you want a boundary means the domain is full real line. What is the boundary? There is no boundary, minus infinity, infinity. So you need a finite domain so that you can make a boundary. Boundary terms are A, B. Okay. If you have an interval, if your differential equation defined only on the interval, finite interval, your boundary is A and B. That is your boundary. So you need some boundary conditions at A and B so that L will be Hermitian. So that is what we will see in the next video.